Welcome again. So now in this module, we will quickly go through the EEIO example. So in the last module, we learned the EEIO model and how it helps us calculate total life cycle emissions and resource consumption. Here we will go through a numerical example for the same. Then we will go through the direct and indirect impacts and then a quick example on that calculation. Okay, so to begin with, let's look at this input output model. So I hope you all now have good familiarity with what an input output model looks like. So here we have two sector economy, agriculture and chemical, and we have the intersectoral flows. We have already seen this example when we were calculating the X star for new final demand. Here now I have augmented the model with two information on CO2 and SO2 in terms of kgs. So that is the emissions matrix, and we have 200 kgs from agriculture sector, 500 kgs of CO2 from chemical sector for producing $1,000 and $2,000 of demand, and $1,000 and $2,000 of through flow, and final demand of 100 and 1350, and SO2 similarly. And then we also have water and air consumption. So water is a resource input that we withdraw from ecosystem. So 50 liters of water is being taken in the agriculture sector and about 100 liter from the chemical to support this much final demand in the economy. And the air, so air is generally used as a circulating factor in lot of chemical sectors for cooling. So we are withdrawing some of the air for the chemical sector as 50 liters, and there is no air. So the first problem I would want you to do is calculate the emissions coefficient. So we had seen the calculation of E bar as E transpose times X hat inverse. So take 30 seconds and quickly calculate these coefficients. So the solution to this problem is straightforward. For calculation of E bar, we can take the transpose of our E matrix. Our E matrix is given as 200, 500, 100 and 250. We take the transpose, and our X hat here is 1000 and 2000. So 1 by 1000, X hat inverse 0, 0, 1 by 2000. So we have the X hat inverse. So for this, the transpose comes to be 200, 500, 100 and 250 multiplied by 1 by 1000. So E bar is equal to, for the first one, this is 0.2 kg CO2 from the sector 1 per unit dollar. This one is 0.25 kg CO2 per unit dollar from sector 2, and the other one is about 0.1 kg SO2 per unit dollar, and the last one is 0.125 kg SO2 per unit dollar. So now we have our emissions coefficient, which means that what is the total amount of emissions that these sectors will generate per dollar output from those sectors. Next, we will do the same thing, but now for resource consumption coefficient. So please take 30 seconds and calculate the resource consumption coefficients for the same economy. So, let us look at the solution for resource consumption. So, here we do not take the transpose. So, we just do R times x hat inverse, and our R is 50 liters of water, 100 liters of water, 0 liter of air and 50 liters of air, and our x hat inverse is 1 by 1000, 0, 1 by 2000. So, this will then become 50 by 1000 and 100 by 1000. This will be 0 of course, and this is 50 by 2000. So, the resource coefficient R bar becomes 0.05 liters of water per unit per dollar output for sector 1. This is 0.05 liters of water per unit per output for sector 2. So, this is for resource water, and then 0 for of course air, and then this one is about 0.025 liters of air per unit of dollar. So, this is air per sector. So, we have the resource coefficient. What that tells is that how much is the total resource per dollar output for each of these sectors. So, for water we have the same coefficient, that is just how the data plays out, 0.05 liters per dollar output for both the sectors, and 0.025 liters of air is required by the chemical sector per dollar of output. So, that is the first step in calculating the total resource and life cycle emissions from the EEIO model. Next, let us see, we want to now calculate the total life cycle emissions and resource consumption for the same system. So, it is the same system that we have already calculated the emissions coefficient. So, if you have to calculate the total life cycle emission, we will use the Leontief model to calculate x star first, which is I minus A inverse times F, and then for E total it is mainly the E bar times x star, and for R total you have the R bar times x star. So, take 30 seconds, we have already done the x star calculation for the same final demand. So, all you need to do is multiply your matrices E bar and R bar with x star. So, the life cycle emissions will be that is equal to E bar. So, our E bar is, we already calculated it as 0.20 and 0.25, 0.1 and 0.125. Our x star we had calculated as 239 and 175. So, we multiply that and your E will come out to be 91.55 kg CO2, and this is 45.75 kg SO2. So, this is basically the kg CO2. So, you multiply this with the x1. So, 0.20 times 239 will tell you total CO2 from sector 1, 0.25 times 175 gives you total CO2 emission from sector 2. So, when you add those, that is the total CO2 emissions in the economy to support these final demand, which gives about x star as 239 and 175. Similarly, we can calculate the total resource consumption. So, total resource consumption will be, so R total is given as R bar times X star. So, your R bar we had calculated as 0.05 liters per dollar and 0.05 liters per dollar, that is the total amount of water from the two sectors, 0 and then you have 0.025 liters per dollar. You multiply it with the new X star that we calculated, which is 239 and 175, and when you do that, your R total star for the new final demand comes out to be 20.7 liter of water and 4.37 liter of air. So, that is mainly giving you the total amount of resource consumption that is required to support the final demand that we had set for the two sectors, which is 100 and 50. So, remember in the life cycle emissions and life cycle resource calculation, that is what we did in the process LCA, that we had this intervention matrix and we calculate the total impact. Similarly, in the economic input output model, your final demand is what is setting the based on the goal of your LCA, that how much is the production that we are going to study. So, for each of that, when we have the final demand, we calculate the total through flow in the economy in terms of X star, and then we multiply that with the resource and the emissions intensity to get the total life cycle emissions. Some people will also call is that the embodied resource. So, we can say that for producing $100 of product from sector 1 and $50 of product from sector 2, the embodied water is 20.7 liter of water or 4.37 liter of air. So, the interpretation is how much is the resource that is required to support that production. So, this gives an idea of how we use economic input output model for getting the life cycle calculation. Next, we will look at an additional calculation from the same model, which is the direct and indirect impact. So, we know that in the input output model, we are of course having some direct impact, but the indirect or the upper supplier impact is also embedded in that calculation. So, we will see what that direct and indirect impact means. So, let us see what is an direct and indirect impacts. For that, we will consider a 3-sector economy. In this 3-sector economy, we have power generation, coal mining and steel manufacturing. So, let us say that we want to generate electricity which has the final demand F1, which is going out of the system boundary, and for that there is a requirement of coal mining or from the coal mining in terms of coal input. Similarly, you might need steel manufacturing because there might be equipment that are based from steel that the power generation sector requires. So, all these flows are the first tier or the direct flows, because these are the direct flows that are required to produce the electricity F1 that we want to make. So, that is our goal. So, the first tier transactions are transaction between one sector and the sectors that provided the output. So, this is what we call as the direct impact in the input output model. Now, let us see what is the indirect impact. So, what will happen, all these red arrows are our indirect impact. The reason why I say it as an indirect impact is that now when the power generation is going to tell the steel manufacturing, I want some amount of equipment from you, then steel manufacturing will see, okay, you want the equipment, so what I need is I need some electricity to support the production of that for that steel equipment manufacturing. So, this is an indirect impact of the power generation requirement. So, remember our original demand for the economy was generation of power, but for producing that power, your power generation needs steel, and to support that production your steel manufacturing now needs electricity. So, this electricity demand from the steel manufacturing is actually an indirect impact of producing power itself. Similarly, coal mining may also say that, okay, you need coal, so I need some electricity to provide you that coal. That is the indirect impact, and for that your coal mining will say, okay, I will go to the steel manufacturing company and I will need some equipment as well. So, all these red flows are actually the indirect impacts. So, these impacts are also called second tier or third tier impact, and these are transactions that arise due to the first tier transaction. So, it did not arise itself, it arises because these sectors now needed to produce more, and for that production was driven by the original demand of the electricity production. So, this is what we call as the indirect demand in the economy because of the original demand. The input-output model is actually very strong because it captures all of these impacts in one concise model of the Leontief model. We can also, so the total effects are actually the sum of both of these direct and the indirect impacts that the model captures. So, let us see how the original model breaks down the direct and indirect impact. So, if you look at the total through flow using the Leontief model, we calculate our x star as I minus A inverse times f. So, okay, that is our Leontief model. If you go back to our power series expansion, geometric power series, whenever you have 1 minus x inverse, we can expand it to 1 plus x square plus x cube, that is the Taylor series expansion. Here your modulus of x is less than 1. So, remember your direct requirements coefficients, most of our AIJ's modulus is less than 1 because it is the ratio of the flow per unit output. So, then we can use the same expansion to expand our I minus A inverse into I plus A square plus A cube. So, we can expand the A matrix, our I minus A inverse calculation, as a Taylor series expansion. So, in this, the first two terms are known as direct impact because I, if you remember, it is just the final demand. So, if you multiply, it is just the final demand that is required in the economy. A is all the flows that are associated directly with the final demand. When you go to A square, it is the indirect flows, because if I write A square, it will be A11 times A11, which means that this was the A11 times F1 was the original direct demand. But if I do A11 times F1, that is the indirect demand or indirect effect that is basically driven by the final demand in the economy. So, using this concept, what we can do is we can break down the total impact that we calculate from the input-output LCA into direct and indirect impact. So, we have the direct as I plus A, we can calculate the total as I minus A inverse, and the indirect is simply we calculate as total minus direct impact. So, sometimes LCA analyst would also want to know what is the direct impact of producing something in the economy and what are the indirect impacts. Lot of the times our indirect impacts are much higher than the direct impacts, and that is why the IO model is really powerful. So, remember, the motivation for the IO model came from that we are missing lot of indirect impacts in the process LCA model. So, most of the time in process LCA we are able to capture second order, third order and fourth order maybe impacts, but even higher order that can come at a to the power 5 or a to the power 6, that is not captured, and sometimes those may be much higher, and hence we are looking at this breakdown between the direct and indirect impact in the input-output LCA calculation. So, next we will see some of the example for the direct and indirect calculations. So, the calculations are straightforward. For the direct economic through flow, we just do x direct equal to I plus AF, and indirect can be indirect economic through flow to support the new final demand can be calculated as x indirect is I minus A inverse F, which is the total impact minus the direct impact, and that is how you calculate x indirect. For the direct life cycle emissions and indirect, all we do is we can multiply our emissions coefficient with the x direct star and ET times x indirect star, that gives us the indirect emissions. Similarly, for the life cycle resource, direct is R times x direct star and indirect is R times x indirect star. In the next module, we will quickly look through the one example for direct and indirect calculations, and then we will go through the hybrid LCA. So, let us go to the summary of EEIO. EEIO is mainly when we augment the economic input-output model with emissions and resource consumption data for a particular economic model that we have collected originally. We then assume constant emissions and resource coefficients for the sectors, and this assumption is mostly valid for the short time period because there is not a significant change in the emissions because the technology has been fixed. Then we can calculate the life cycle emissions, which is the embodied emissions for product, or life cycle resource consumption, which is the embodied resource for a product. using the Leontief model and the emissions and resource coefficient. So, we already saw an example of this in the module 16. So, I hope that becomes very clear to you. Then we can also do the direct and indirect impacts which are embedded within the total life cycle impact. So, we saw that we can separate out the direct and indirect impact by doing a Taylor series expansion of I minus A inverse. So, we will have a example problem to solve for the direct and indirect impacts for the LCA. And mostly we are using Taylor series expansion. So, the first two terms which are I plus A gives us the direct impact, and then the rest of it is indirect impact. So, with that, that is the end of environmentally extended input output model. We will see some problems, practice problems that you can go through to understand this model much better, and we will next go to the different LCA model of hybrid LCA. So, thank you for attending this module, and I will see you in the next module.